let's get going.
Let me sit on that for a while.
Yeah.
Right, revision of angular momentum. You've seen it before, but in the context of spin, it is quite useful. Spin is not angular momentum, but it shares enough mathematical properties with it that we need to look at it again. And what is also a higher purpose of this lecture is the introduction of a link between fundamental symmetries of physical reality and fundamental conservation laws. When you were at school, and then in the earlier years, you were given conservation of energy, linear momentum, and angular momentum as fundamental laws without derivation. They are not in fact fundamental, and they can be derived from basic symmetries, and we will derive the conservation of angular momentum today. So let us make a very straightforward observation that our physical reality here is invariant under the rotation of the coordinate system. Right? So rotational invariance. Is our first topic. And what do I mean by that? I mean, if we take an isolated finite physical system somewhere into intergalactic space where there are no gravitational or electromagnetic fields, we measure its energy and record the reading. If we rotate the system ever so slightly, or even if we just rotate the reference frame of our description, then the energy of the system should not change. And that is rotational invariance. In other words, the universe, at least from the observations so far, appears to be isotropic. Every direction in it is as good as every other direction. What does that mean for us? That means if we take some wave function, psi, and we apply a rotation to it. So we turn the corresponding object and we release it, so it remains stationary. So we apply some rotation operation to our wave function. The properties must remain unchanged, and that includes energy. So if we now calculate the energy of this rotated wave function, it must be the same as the energy of the original one, assuming we rotate the entire system or we rotate the reference frame underneath it. So our energy that was previously psi h psi must not change. And so if we replace psi with its rotated version, what we are going to have is, on the right we will have the r psi, and on the left we will have the conjugate transpose version, so we would also have to conjugate transpose this operator. So we are going to have this psi r conjugate transpose h r psi. That's the rotated version of psi on the right, and that's the rotated version of psi on the left. Now, what do we know about rotation operators? You have already seen that in your mathematics courses. I will just give you a brief example of that. In 2 dimensions, we have cosine alpha and then minus sine alpha, then sine alpha, cos alpha. Let's think about what would happen if we do a conjugate transpose of this. We have cos remaining unchanged, and the minus would jump over here. So I would rewrite that again, cos alpha, sine alpha, and then minus sine alpha, and then cos alpha here. That is actually the same as the original matrix with the alpha swapped for minus alpha. Right? So if that was our R conjugate transpose, then that is R of minus alpha. Right? cosine does not depend on the sign of alpha. Sine is odd, so we can pull that minus in here. This will be a minus alpha. We can pop a minus there and put a minus alpha in there. In other words, for a rotation operator, the conjugate transpose is equal to inverse, which is quite handy for us here. So we can say, okay, that is psi r minus 1 h r psi. Okay, let us do a little bit of philosophy about it. So this must be true for any rotation, and more importantly, this must be true for any wave function. So what I'll do is I will rewrite that and that as an equality. So h here, and then psi, and that thing in the middle, r minus 1 h r, and then another psi. Not forgetting any hats anywhere here. Okay, this must be true for any conceivable wave function. So what it must be true for, therefore, is the operators themselves. So what follows from this is that h is equal to r minus 1 h r. Okay, what does this mean? Well, so far not terribly clear, but let us multiply this on both sides by r. We will have RH on the left, r will cancel with r minus 1 on the right, so what we are going to have is RH equals HR. And then I will move that over to the right hand side and conclude that HR minus RH is 0. Who recognizes the pattern here? This is a commutator. So we conclude that the Hamiltonian commutes with the rotation operator. But what does this mean? Well, let us think a little bit more about this. Let us look at the time dependence of whatever property it is that corresponds to this rotation operator. So its physical observable would be psi r psi. So let us consider now this physical observable, and let us now look at how it changes with time. So d by dt of this physical observable in light of what we have just concluded about all of these operators. Okay, standard product rule for a triple product. So we have d by dt acting on psi, then r, then psi. R itself is time independent. Remember, it's a fixed rotation, so we will have the middle term missing here because the derivative of r with respect to time is 0. And the final term of the product rule, psi r and then d by dt psi. Okay, but of course we know what d by dt psi actually is. That's Schrödinger's equation. So, reminding you, d by dt psi is minus I h psi. I'm missing the h bar and other fundamental constants, right? We are working in atomic units here. Okay, so what we need to do is we need to plug that here and to plug the conjugate transpose version of it there. Let us do that. So that will be, conjugate transpose of that will be psi h with an I in front, and then psi with an R, so h r psi, and the other bit here is psi r and then minus ih psi. So putting a minus here, I psi r h psi. And finally, we take psi's out of the bracket, this one on that side and that one on the other side. This is I psi, and then H R minus R H, and then psi here. And of course, we've just demonstrated that that is 0, so that is 0. Whatever observable it is that corresponds to this rotation operator is apparently conserved, because its time derivative is 0, it doesn't change. We have just discovered a conservation law. Now notice that we haven't had to do too many assumptions to arrive at this conservation law. We said, okay, one thing our eyes are telling us about the reality we are living in is it's isotropic, that fixed rotations do not change energies of physical systems. We have put that into the quantum mechanics framework that we know. We have done a few transformations, and we arrived at a conservation law for a quantity that we haven't yet found out what this is. So the second item on our agenda today is to find out what are this rotation operator that turns our wave functions actually is. So item 2, rotation operators. I need to give an aside here about rotational and translational conventions. Remember how we translated one-dimensional functions. We had our coordinate, here x, we had some function, here f, and then if I had a function that was f of x, so let's say some kind of peak, this is my f of x, then if I wanted to translate my function forward down the axis, so to put it here somewhere, that was f of x minus some number, where the number here is the shift, right, by which we want to move it. Likewise, if we would like to rotate a function in 2 dimensions, so I can draw the corresponding diagram in 2D, if that's our x and that's our y, and we had some function of those 2 variables, so sitting here somewhere looking at it from the top. So if that is our f of phi, then if we would like to rotate it by some angle alpha, so say that is our angle, and we would like our function to sit here, then that is f of phi minus alpha. Now, the second thing that I must mention is the convention for what is meant by a positive rotation. Blame the ancient Greeks for this, but positive rotations in physics are counterclockwise. Somebody has decided at some point that a rotation by a positive angle is counterclockwise, and that's the ISO standard that we now have to deal with. Okay, so I will first give you an interesting relation, and then I will prove it. Turns out, if we take a psi and it's a function of something, and psi of phi minus alpha, so the rotated version of a particular wave function is the result of action by the following strange looking operator, minus alpha d by d phi, acting on psi of phi. Now that's a lot to take in the first time you look at it. What do we even mean by the exponential of a derivative? Let me expand this in the Taylor series, and then it will become clear that that's just an abbreviation for a certain series. I will remind you what the exponential of x is. It was a sum n from 0 to infinity, x to the n over n factorial. And let us do exactly this to that, and we will be able to demonstrate that we do in fact get our function rotated. So I will use that as a reminder, and I will say, okay, this will therefore be a sum from n0 to infinity. Then we will have minus alpha to the power n over n factorial, then dnth by d phi to the power n, all of that acting on our function psi of phi. And you can see exponential looked kind of weird, but once we expanded it in Taylor series, there's nothing special about it. That's just the nth derivative of our wave function. And so operators of this type you will encounter a lot where there is an exponential of some instruction. And once you just open it up in the Taylor series, that's simply an instruction to apply whatever's here repeatedly and to combine the outcomes with some coefficients. Okay, let us take a good look at what we have here. What, of course, must also be present there. So that is our derivative. That is the minus alpha. So let us continue writing that. And what we are going to have is I will put this nth derivative there. So this is our n0 to infinity. Then to make it more familiar, psi of n of phi over n factorial. So I have collapsed that derivative into a different notation. So n primes here signifying differentiation, computed at the point phi, and I will put the minus alpha to the n in front. But that actually is looking exactly like a Taylor series, right? Look, there's the nth derivative of psi and the n factorial in the denominator, and that is the argument at which the function must be evaluated. So this is in fact psi of phi minus alpha, right? If you perform that calculation, you will see that that is what this Taylor series corresponds to. So the exponential of a derivative turns out it is a translation operator with respect to the corresponding coordinate, and if the coordinate happens to be angle, then of course that's a rotation operator. Okay, we have found how to do rotations by operators. And the final thing that remains now is to translate it back to Cartesian coordinates, to turn this d by d phi back into xyz and to find out what it looks like in xyz. Another reminder about polar coordinates. Remember that x was our cos phi and y was our sine phi. We will have a lot more of that in due course, and I've been tormenting you with those coordinate transformations in your mathematics course for a reason. So if we take df by d phi, well, that is the standard chain rule for partial differentiation. That's df by dx, dx by d phi plus df by dy, dy by d phi. And we know what dx by d phi is and dy by d phi is. So that is going to be dx by d phi minus r sine phi minus r sine phi here, and then df by dx plus r sine phi derivative, so that's r cos phi, then df by dy. And finally what I'll do is I'll take f out of the bracket, and I will also observe that r sine phi is y, so this bracket is minus y, and that bracket is x. So what I have here therefore is x d by dy minus y d by dx acting on f, this time of xy. All right, so we have now found an explicit Cartesian expression for our rotation generator here. So if that overall exponential is called rotation operator, in group theory, whatever's under the exponential is called the generator. Okay, that's our rotation generator. And now there's another historical convention, and who to blame for that? Probably Wigner. We have to put a complex unit in front of this. So our rotation r by an angle alpha is now the exponential of minus I, and so it's this minus I that is historical, L z alpha, and if we have a minus I here, we must have the corresponding I over there, where the Lz now is minus I y d by dx minus sorry, that should be x d by dy, because we need to swap it around. So x d by dy, catching all the minuses, minus y d by dx. So if we put that here, minus I and minus I gives us the minus swaps these two terms around, and we have that property there. Okay, so we have found an explicit expression for the rotation operator, and this, because we worked in the xy plane, is the rotation around z. So we put a z there. Likewise, if we perform the corresponding transformations for rotations in the xz plane and the yz plane, we will find that the corresponding generators for the rotations around the x-axis and around the y-axis are as follows. Ly is minus I, then z d by dx minus x d by dz, and Lx is minus I, and then y d by dz minus z d by dy. These are quite obscure. What on earth are they physically? Because we have just derived them mathematically, and there are a great bunch of derivatives, and if we put those derivatives under the exponential, then they rotate something. Let us think about what they physically mean. And for that, we need to go into classical physics and work our way through the classical physics until we see exactly the same expressions, and then we would be able to find out what they mean. Okay, so item 3, connection to classical physics. And actually to physics to begin with. Let me remind you what angular momentum had been in classical physics. It was L equals R vector product P. And reminding you again what a vector product is, it's the three coordinate orths I, J, K, then X, Y, Z, and then Px, Py, Pz determinant. Let us open this up and put it into a vector, right? So angular momentum is a vector. So our I is that times that times that, so the main diagonal product, and then the counter diagonal product, that is Pyzi. So main diagonal with a plus, the triangle with a minus. So the first element of our vector here is y pz minus z py. If we likewise do it for j, j participates in that triangle with the minus, and in this triangle with the plus, so zpx minus xpz I assume you haven't forgotten how to calculate 3 by 3 determinants. And then the final thing for k is that with a minus and this with a plus, so xpy minus ypx. Coordinates and momenta. How do we move from classical physics into quantum physics? We take canonical quantities such as coordinates and momenta and we replace them with the corresponding operators. And let me remind you what they were. X operator was just multiplication by x, y was multiplication by y, z was multiplication by z, but the momenta were differentiation. Px was minus I d by dx, and likewise for py and pz. Now we have py minus I d by dy, and pz is minus I d by dz. Well, let us put them into those expressions. Turns out we will obtain exactly the equations that we have got there from our symmetry theory. So the x component of this there, now it is an operator, Lx is ypz, so minus I times y times d by dz, minus I y d by dz, minus zpy, so here z d by dy. And this is exactly what we had when we had derived these rotation generators from symmetry. And so we have made this very important connection. Notice what we did. We have started from a very fundamental symmetry observation, that universe is isotropic. After a bit of philosophy, we realized it corresponds to a conservation law for a certain quantity we couldn't yet identify. We then looked at what that quantity is, and after a bit of mathematics, we said, okay, that quantity is the exponential of these operators. And of course, if the exponential of something is conserved, then whatever underneath it is conserved. So it is these quantities that are conserved. We then went back to our classical physics and managed to fish out a known quantity and translate it by some mass into exactly the same form, and realize, aha, that's angular momentum. So from just the isotropic nature of free space, we have discovered the concept of angular momentum and we have discovered the corresponding conservation law. This is very deep. This is called Noether's theorem, which states that any differential symmetry of a physical system yields a conservation law. This was for rotation. If you do exactly the same for translational invariance, because of course universe is uniform, every position is as good as every other position, if you repeat this mathematics for the translational symmetry, you get conservation of linear momentum. And if you repeat this for translations in time, you will get conservation of energy, because every time point in our continuous history, from the physics point of view, appears to be as good as another. Time appears to be uniform, continuous, and the rules by which reality evolves do not appear to change with time. After you work through that, it turns out that that leads to conservation of frequency, and as you know, frequency corresponds to energy in quantum mechanics. So the three great conservation laws that we have in physics correspond to the three great symmetries of physical reality. I will not prove this fact, I've sort of alluded to it in the very first lecture, but if you also add Lorentz invariance and special relativity to the mix, then you also get spin. And this is where spin fundamentally comes from. Okay, so we have now derived ourselves angular momentum and the corresponding conservation law. You have, of course, explored it in the past, all of those horrible LM eigenfunctions and raising and lowering operators. I will simply remind you what they are, because we will be building the theory of spin in connection to these operators. Okay, so item 4 is properties of angular momentum. One important property is commutation relations. They are important for reasons that I unfortunately cannot cover in this module, because you don't have Lie group theory. You only have finite groups in your crystallography and molecular quantum mechanics, but there are groups of continuous transformations like rotation groups, which are differentiable rather than discrete, and they have these commutators as a central feature of the corresponding generators. So trust me, that's an important thing to do, but we must work out the commutators of, for example, Lx and Ly. So Lx operator, Ly, what is the corresponding commutator? Now you can imagine that I am setting myself up now for quite a lot of mathematics. Lx is this monster, Ly is that monster over there. I always approach this task with some trepidation, but once in your life you must do that. So let us see if Kuprov still has what it takes to calculate this commutator and not make any arithmetical mistake in the process. Okay, so we are dealing with minus I pops out in front, so squared, and then a giant bracket, so Lx times Ly, that will be y d by dz minus z d by dy times Ly, and Ly we have there, z d by dx minus x d by dz, and that is with the plus, so I remind you that a commutator b is ab minus BA. So this is the AB part, and we must also do the BA part there, and I think I should continue writing in that direction, because otherwise we will run out of space. Z d by dx minus x d by dz times y d by dz minus z d by dy. Okay. Now we open all of that up and we try to simplify. Certain things will simplify easily and others will get mixed up, because, for example, the derivative of z with respect to z does not commute with the multiplication by z, so we will have to be careful here. Okay, minus I squared is just a minus. So we keep that minus in front of the bracket, and okay, y d by dz acting on z d by dx, y d by dz, z d by dx, so that's that times that, minus y d by dz acting on x d by dz, that is this times this and that times that. So now minus z d by dy acting on z d by dx, and finally plus z d by dy times x d by dz. And this is our first term here. Let me just check that. Y d by dz, z d by dx, y d by dz, x d by dz, z d by dy, z d by dx, plus z d by dy, x d by dz. Yeah, this is our first bracket here. Okay, now we have z minus in front, so that keeps the minus. Then we have a minus and a minus. That gives us the plus for the second bracket underneath it. So plus, and opening up that z d by dx, y d by dz, minus z d by dx, z d by dy, then minus x d by dz, y d by dz, and plus x d by dz, z d by dy. Okay, double checking. Z d by dx, y d by dz, z d by dx, z d by dy, x d by dz, y d by dz, x d by dz, z d by dy. Okay, now let us open everything up, and a few things are going to cancel. So not forgetting that minus in front. What we are going to have here is a few interesting things. Derivative with respect to x can be swapped with multiplication by z because it doesn't act on z. It can also be swapped with the differentiation with respect to z. So long as operators act on independent variables, they can be swapped around. So we have minus y d by dx, d by dz, z. And with this object we are stuck, right? We cannot permute these two because there's a derivative. Plus y x d by dz, d2 by dz squared, right? Second derivative with respect to z. Then minus here z squared d by dy, d by dx, plus we have zx d by dy, d by dz, and I should not be forgetting this minus sign, so minus here, plus here, therefore plus here, and therefore minus here. Okay, that is our first bracket, and then repeating our second bracket there, plus zy just come out in front, zy, then d by dx, d by dz, then minus, and keeping it here, we have z squared, d by dx, d by dy, then minus xy, d2 by dz squared, plus, and here we have that same strange crocodile we couldn't get rid of. It's x d by dy, and then d by dz, z. Let us see what is going to cancel. Z squared, d by dy, d by dx, here with a plus, z squared with exactly the same derivative here with a minus. Gone. Yx d2 by dz squared with a plus, xy d2 by dz squared with a minus. Cancels. Then zx derivatives with respect to y and z. And let's see what we have here. That probably leaves. That probably leaves. So, okay, so far I think that's as much as is going to cancel. Zy, zx, y, z. Let's see if that disappears. No. Okay, we are as good as it'll get. Now, let us take a closer look at this thing here. What is d by dz? Remember that there's always a function in front of any operator. So, therefore, d by dz doesn't exist in isolation. It acts on some function, so there is an implicit f of z in front. And the operator says, well, okay, multiply it by z first and then take a derivative with respect to that. So we must here use product rule, which is then derivative of z times the function, so f of z, and plus z d by dz f of z. And so if we take f of z out of the bracket here, then that is a unit plus z d by dz. So in order to swap z and its derivative around, we must not forget this fact that there's a unit popping out here. All right, let us do that. I have this minus y d by dx, and then here it's the unit operator minus z d by dz. That's gone, minus zx d by dy d by dz plus zy d by dx d by dz. And then the final thing here is the plus z x d by dy, and now again this is 1 minus z d by dz. Let us see if anything else now cancels again. Notice here y, z, x and z with a plus. Z, y, x and z here, right? Zx dy by dz. So let's see, we have x d by dy, z d by dz. So x z d by dy d by dz. That should of course be a plus from there, so that's a plus and that's a plus because there's a plus there. Okay, so z y z x with a minus, z y z x with a plus. That will disappear and this will disappear. Then x z y z with a plus, x z y z with a minus. This disappears and that disappears. And finally what we are left with is x d by dy minus y d by dx. And if I pop a minus I out in front, minus I, then there will be, should I pop the minus I out in front? Yes. I'll put an I out in front. And then what I have in the brackets here is minus I, and they will have to be swapped around, y d by dx minus x d by dy. And that, if we compare it with the LZ operator, here, minus I x d by dy minus y d by dx. That is ILZ. And I still have what it takes to perform this particular derivation. I think I've just about made a mistake at some point, but then I caught myself with the correct sign there. And that gives us the plus, so that is another minus in here. And yeah, we're good. So the conclusion is that this commutator that we've just computed, Lx commutator Ly, is ILZ. And likewise, I invite you to repeat this process at home. Turns out that Ly commutator Lz is ILX, and Lz commutator Lx is ILY. From the fact that I remember these relations off the top of my head, you can conclude that they're probably kind of important. And we will be building the theory of spin based on these commutation relations, because the algebras of spin and angular momentum are isomorphic. The final thing that I need to remind you about is that these operators had eigenfunctions, that we had the following relations. We had Lz acting on its eigenfunction. You've seen it in your angular momentum course. So spherical harmonic of theta and phi, and that pops out the projection quantum number for it, theta and phi. And these are responsible for the shapes of atomic orbitals. So S is spherical, P is H-shaped, D, and so on. And then there is the total momentum operator, L squared, which is Lx squared plus Ly squared plus Lz squared, which is conserved under rotations of the coordinate system. And likewise here, L squared acting on YLM, theta and phi. You had L plus 1 by Lm, theta and phi. And in the language that you had at school, L was the orbital quantum number and M was the magnetic quantum number. This determines the orbital type as PDF, and that determines the cell within the orbital type. And L had to be positive, or equal to, greater or equal to 0 and an integer, and M was from minus L to L. For example, for L equals 1, you have the p orbital, and then you have 1, 0, and minus 1, the 3 cells inside that p orbital. And the very, very, very final thing that I will mention is these two special operators that you've also seen in your angular momentum course, the raising and lowering operators, I, L, Y, that take the projection quantum number up and down by one click when you apply them. So what we will do in the next lecture is use this revision to build a semi-empirical theory of spin. So this was done in 1920s or thereabouts, starting from about 1924, when people realized they have extra splittings in the spectra of atoms, and the assumption was that spin is yet another kind of angular momentum. And what we will do in the next lecture is build the corresponding mathematics by analogy with these commutation relations. We can say, well, okay, unlike angular momentum, spin has a fixed number of energy eigenstates. Can we build some matrices that have exactly the same commutation properties as the corresponding angular momentum operators? And it turns out that we can, and that leads to a serviceable semi-empirical theory of spin, which has the practical benefit to us is that I don't have to drag you through special relativity to derive spin properly. We will derive it by analogy with some things that you already know. Okay, summary of the lecture. Every symmetry of physical reality corresponds to a conservation law. We have found the rotational version of that law. It leads to conservation of angular momentum. We have found, through some pretty nasty algebra, explicit expressions for rotation operators. We first observed that it must look like that. We then converted into Cartesians and realized that the d by d phi, depending on which angle you're rotating it around, corresponds to these three. We then dipped into classical physics and realized that those three in fact do correspond to the three Cartesian projections of classical angular momentum when you quantize it by replacing the quantities with the corresponding operators. I managed just about to not make an arithmetical mistake in deriving this commutator, and we will be using these commutators in the next lectures to deal with spin. Any questions?
Are you going to make us do that in the exam?
No.